invitation. And so this is stuff that I did probably around 2016. It's a little bit old, but the reason I decided to talk about that is because some people in the audience have heard some of my more recent talks, so I thought I'll go back to something a little older. And there is some loose ends at the end which I would like to come back to, so maybe this will trigger me to start working on it again. And another third reason is that this has a kind of a Hawking-like vibe to this, so I thought it's I thought it would be a good idea to.
You call it the Krishnan-Hawking boundary.
Oh no. I would call it the Krishnan boundary term.
Sorry. I apologize.
No, actually, it's Krishnan Raju boundary. Krishnan Raju. I mean, it's yeah. Anyway, so So the first 10 slides at least should be extremely elementary. So I hope that if there are students, etc., this thing, it should be very, very clear. The last part is a little sketchy, and I might have also forgotten some of the things, but hopefully it's not too bad. So anyway, so the basic question that we have is that so the Gibbons, any variational problem, any equation of motion that you have, if it comes from a variational principle, we would like to, so the way in which it is set up is that if you vary the action, you get boundary terms, and the boundary terms typically depend on the variation of both the field and its derivative. And if you set both of them to 0 at the boundary, then there is no dynamics. So you have to make sure that you set only one thing fixed at the boundary, and you get some well-defined variational principle. And in order to do that, typically you have to add an extra boundary term. And that is what gives rise to Dirichlet or Neumann, depending on which, whether you're holding the field fixed or the derivative of the field fixed. So this is typically how things work for particle mechanics and also for field theory. But in the case of gravity, the standard boundary term, so the standard boundary term that we have is this Dirichlet boundary term. And which basically holds the boundary metric fixed, and then you have a well-defined variational problem.
Sorry, let me understand this. So suppose I consider just the final path integral for a particle.
Yeah.
Okay.
Yeah.
So then I fix the initial position and the final position.
Correct.
So two conditions.
That's right. So I'm
consistent with the fact that Newton's law is second order in time.
Right.
So here, I mean, in let's say in a black hole context, I understand in the Gibbons-Hawking thing that there is some boundary. Let's say Euclidean. Euclidean black hole. So it has to be smooth at the black hole
horizon. Right.
And therefore, if I specify both Neumann and Dirichlet, then it will generate.
Yeah, correct. Right. That's right.
Therefore, I can only.
Right.
But how can I make this statement like a generic statement?
What is the statement that you're not happy with?
Makes the the statement that you made, not the one in
so
that you cannot specify two boundary. Why can't I specify?
No, so I'm thinking of it as having only one boundary. The way you're saying it has two boundaries, right? I'm just saying that if you just specify one boundary, so then either you have to specify two boundary conditions, of two second derivative.
Even if it is disconnected boundaries, I still specify Dirichlet on both. That's what.
Yeah, that's right. Yeah.
So just a more general point, I think, if I understand, is that okay? You have some bulk action.
Yeah.
And you want the variational principle to give rise to the equations of motion from that bulk action.
That's right.
That typically will give rise to some boundary terms.
Right.
Which should vanish.
Right. Yeah.
And then that determines the boundary conditions.
But there still there is you still have the possibility of setting both Dirichlet and Neumann boundary conditions and
together.
No, I'm saying
either.
Suppose there has to be a reason why I cannot. For example, I could do Dirichlet here and Neumann here and so on and so forth. So the point is that there is only one boundary.
Yeah. So I mean,
And with Dirichlet condition, something else remains, and that I cancelled by Gibbons-Hawking.
Yeah.
Okay. Just to be. Because it's second order.
Yeah.
So therefore, I can in principle specify if it is a Cauchy problem.
Correct.
I can in principle specify
Yeah.
both the field
Yeah.
and the derivative.
Yeah, so and in order to solve the classical system completely, that's what you would do. But I mean, in some sense, it is what do you, what kind of, what do you integrate over is the bit that you are leaving open when you do the, what you, if you hold
so
fixed.
You have in mind some smooth thing
Yeah,
at the other
yeah.
end and not going all the way to infinity.
So for instance, I can think of most of these things, most of the statements that I'll make, especially later on, will be in Euclidean setting.
Yeah, that's
Yeah, Euclidean or more like complexified.
Euclidean with one boundary.
Yeah.
Then everything is.
Yeah, yeah.
Because then it's not in the Cauchy product, it's a Laplace.
As
Yeah.
you're saying for hyperbolic equations,
Yeah, I mean
you
they
should be able to specify both of them. But even there, if I at least think about it as a action variation, then as you said, I have the action in time as well. See, because to derive the equation of motion from the action.
Yeah, so maybe I'll show you an example of the particle mechanics example. What I have in mind will be clear when I look at the particle mechanics example. So, so I think I have said everything I wanted to say here. So, yeah, so this is, so what you're talking about is setting the boundary at the bottom here, boundary condition here as well. So this is kind of, I'm thinking of this as a Dirichlet problem, but of course this is in time direction. So let's say you have a particle mechanics problem of this type, and if you hold q fixed at t, we have a well-defined variational principle. We end up finding Newton's laws through this, and so this is basically so when you do this, you get this boundary term here, and this boundary term, one way or another, we have to get rid of in order to come up with the equation of motion. So this is a statement. So, and when you do that, there are two ways in which you can do it. One is that you either set q dot equal to 0. If for this particular, this is the Dirichlet problem. So note that this is typically what we call the Dirichlet action, or yeah. So and then there are two ways in which you can get rid of the problem. One is either to set q dot equal to 0, or you set delta q equal to 0. So the delta q equal to 0 is what one typically refers to as the Dirichlet problem. So
I was indeed thinking about the lower end of the integral.
Yeah.
And then you will have another contribution with minus q dot delta q at time t equal to 0 or something.
yeah, yeah,
And then my path integral typically is written as a function of two things.
correct.
One is the Dirichlet value for q naught,
Mm-hmm.
and then the other one is some q1. That
Yeah,
was-
yeah, yeah.
And I guess I have never thought about this, but I guess in particle mechanics, you need not think of the equations of motion coming from varying the action, extremizing the action, subject to the variations vanishing at the two ends, which is delta q vanishing. But also,
Yeah,
if instead,
Yeah,
could say
you could
that
have like
q dot
exotic.
vanishes at one side.
yeah, yeah. So that's the,
Okay.
yeah. So there are parallels to this in field theory, general relativity, and so on. So and we'll talk a little bit about it. So this is that. Yeah. So let me look at here. Yeah. So what we can do. So this is that is if you want to call it the Dirichlet version of particle mechanics, and you can talk about instead of holding the position fixed at t, we wish to hold the velocity q dot fixed. This is at least a problem one can ask. And the way to do that is you just add like this piece here, and then what happens is instead of q dot delta q, you have q delta q dot as the boundary term, and now you have the possibility that you can hold q dot fixed to anything, and then you have again a well-defined variational problem in the standard sense. So so that's basically that, and it's so what the price that we paid for it is that we changed the boundary term here. So in the case of particle mechanics, of course, the boundary term is the bulk action is automatically in the Dirichlet form, so there is no extra term that needs to be added. But here we have to add something else. So I'll look at this in a slightly different notation, let's say, and the way so instead of talking about velocity and position, now I can talk in terms of canonical momentum, a boundary canonical momentum, where this pi t is defined in this way, and you can check that for the particle mechanics problem, pi t is just q dot. So this really doesn't change anything, but the value of doing this is that this kind of generalizes easily to other settings where the velocity is not a particularly well defined idea. So, so the Neumann action in this language, it basically looks like this. And what we have effectively done here is something, a boundary Legendre transform, and which is again something that is kind of interesting for when you have boundary in ADS-CFT and so on. So this is our extremely simple boundary Neumann action for particles in this in this momentum language. So yeah, this is what I was just saying. This is that in the particle mechanics case, this re-expressing this boundary velocity in terms of the boundary momentum is not particularly interesting or important. But it turns out that in the case of gravity, this is I think it is essential, because in the case, the velocity, the natural velocity is basically a derivative in the metric, and the derivative in the metric is not a particularly covariant idea. So we don't want to use that as our definition of Neumann. So that's the basic reason why we like to use this. So yeah, and this actually allows a natural generalization. So this is our main motivation for considering this formulation of Neumann, and it leads to a very general alternative to the Gibbons-Hawking York boundary term. So let me just write this. So this is the standard Einstein-Hilbert action, and the variation of the bulk piece gives you this term. I haven't defined what this theta and theta ij are, but I'm pretty sure that most of you know what it is. It's extrinsic curvature, and the crucial point here is that the bulk equations you get from here, but you need to make sure that these guys somehow die out. And just by setting the boundary metric, this is the induced metric on the boundary, setting this to 0 does not guarantee that the boundary term dies off, and that's something that we would like to get rid of in order to get a well-defined variation problem. So this is what was done by, sorry, yeah.
Okay, so delta theta is the variation. So this boundary term is normally just the extrinsic curvature on the boundary is variation, the variation of that term.
Right, that's right. So no, but so here notice that this is coming entirely from the Einstein-Hilbert piece.
Oh,
So, yeah.
Oh, I see.
Yeah.
So to this, normally
Yeah.
we would add a
Yeah, exactly.
term which would cancel.
Exactly. Yeah.
This is after doing the partial integration.
Yeah, that's right. There is a boundary, but there is no boundary term. That's the situation here. So the remedy for that is that you add this piece. This was first written down by York, and then also by Gibbons-Hawking in a famous paper. And the variation of this, the combined thing, you end up finding that, if you go through the algebra, you find this epsilon is just I'm keeping the boundary time-like or space-like, it doesn't matter. But apart from that, it's just the standard variation of the Gibbons-Hawking York action. And you find that if you set delta gamma ij equal to 0, then you find that there is a well-defined variational principle, and we get the equations of motion. So yeah, so this is the standard analog of particle mechanics action for gravity. The point is that just the Einstein action is not enough. So now we can, based on what we were talking about before about the Neumann particle mechanics, we can go ahead and talk about this pi ij, which is the boundary the partial derivative, functional derivative with respect to the boundary momentum, boundary metric, induced metric, and then you get this quantity. And this is the natural quantity to hold fixed at the boundary. And if you so the Dirichlet variation now can be written in this way. So I mean, because it's exceptionally simple, that's the reason why I'm going through everything. But this part is completely simple. So this is so you do this, and then you find this. And the natural Legendre transform, the analog of the Legendre transform that we did before for the particle case, is this is your Dirichlet piece, and then you do the corresponding Neumann, the corresponding Legendre transform piece, and this is what one would call the Neumann action. And if you do this, we would expect to be able to hold this guy fixed, and this is a natural candidate for momentum. And if that is held fixed at the boundary, you should get a good variational principle as a claim. Sorry?
That's the Brownian existence.
Which, yeah, I think it is called that. Yeah, I think it is basically the thing that people sometimes call K or something. Yeah. So theta is called K, and the Kij, this is kind of like the, yeah.
This pi upper ij contains the factor of root gamma.
Yeah, it contains, that's correct.
That is why you.
Yeah, that's right. There is a root gamma here. Yeah. So now the variation of this, you can immediately convince yourself that this has this form. So holding pi ij fixed becomes a well-defined variation problem. And so now the action, so this is what we call the Neumann problem of gravity basically. And if you write down the explicit action, it takes this form. And for contrasting it with the Dirichlet, so the Dirichlet problem, I've also written down the action here. So the basic difference is that the coefficient here has changed. And I think the big reason why, I think the basic reason why it was missed in, for, you know, it's, or at least missed since the invention of this is because d equal 4, it's trivial. So it just so happens that it doesn't show up in d equal 4. So the standard Einstein-Hilbert action with no boundary term has a Neumann interpretation in 4 dimensions. So, I think, so this is, I don't know exactly this, I don't know whether it is somehow deep or something, but it's just, calculationally it just comes out of it. So, yeah, that's that.
Just to understand, you're saying if you took in 4D just the standard Einstein-Hilbert action,
That's right.
it gives rise to a well-defined variational problem if the boundary condition is that the extrinsic curvature.
Yeah, that particular combination is, yeah.
vanishing.
Yeah, that's right.
Field.
That's right. So, yeah, that's the statement. So, yeah, so I mean, this is after that, you know, my talk is going to be a little bit sketchy after that. I just hope that this part I think is completely trivial and I could explain in detail, but the rest I'm slightly shaky about what happened. It's 1.5 years ago. But
So just to say one thing, I mean, this, you know, switch between Dirichlet and Neumann boundary
Yeah.
conditions, of course, is the same as in ADS-CFT.
Yeah.
It's the same as switching between standard quantization
yeah,
to the alternative quantization.
yeah, but that's it.
exists.
But it's in the some fixed ADS background where you typically it is done for a scalar field in some mass range. So in
I was just wondering that if you did it for a graviton.
yeah, so if you do it for graviton, that's something that actually that's one of the questions that I was kind of, you know, maybe you can yeah. So I mean, so the point is that the graviton is you know, it's in the you know, unitarity bound and all those kinds of things will come up. So for a scalar within the, you know, if to do the Legendre transform.
So you're saying this Leonov-Witten window
Yeah.
may not exist. for
Yeah,
graviton.
yeah. So I mean, it's outside the window basically.
It's out.
Yeah. So the stress tensor and the metric kind of play the same role as.
So therefore there is no alternative quantization.
Well, I mean, I've kind of started thinking about it a little bit very recently, as actually after I agreed to give this talk. But I think there is probably more to be said. I haven't really explored it too much, and one of the reasons I wanted to go back was kind of partly because of that. But yeah. So, but yeah, maybe I think you will have more to say. I mean, I don't fully. There are various things I don't understand there.
The window for the scalar.
Yeah.
It just says the square root
Yeah.
thing
Yeah.
has to be between 0 and 1.
I think it depends on D, the dimension that we work with. So this d by 2 minus something. I mean that standard.
Yeah, I'm saying the square root of d square by 4 minus m square r square.
Right.
This square root has to be between 0 and 1.
That's right. Yeah, that's the statement. Yeah.
And this window may not be available for gravitons.
Yeah, that's
Okay,
right.
I don't know.
Yeah. So also the thing is that there are two. I think there is a distinction to be made between the fluctuations of the graviton as well as the graviton and the graviton just by itself. In the graviton of the metric as it stands, because I think perturbatively, I think you can probably say a little bit more. So if you just do a Legendre transform with respect to the full background metric, I think that's a little bit more. That's a more.
No, I was thinking of just the graviton.
Yeah, the fluctuation you mean.
Yeah. So for which you know for
Yeah, fluctuations. I think all the statements that you're saying, I think are correct. I think. Yeah.
I mean, it's not clear that you get a consistent or rich enough dynamics if in ADS you host what we normally call as the non-normalizable mode of the graviton.
Right.
The normalizable one.
Yeah. So it's So the one thing I would say is that I'll say a bit more. The status in ADS is not very clear to me. So yeah, I mean there is a question of normalizability of the fluctuations. That's one thing, and the second. But the one thing what we do find is that you know, the holographic renormalization goes through perfectly well. So I'll say that more about that. Yeah. So yeah, so some curiosities, if you will, is that so this is in d equals 3, the Neumann boundary term is basically this 4 minus d by 2k is just half k, and that's a particular combination that people have tried before for other reasons in flat space as well as in ADS in various contexts and in the ADS case it has been noted by Bagnados that it is basically the Chern-Simons action but with no extra terms in the boundary at all. So in d equals 3, this has been noted before. And in 4 dimensions, our boundary term identically vanishes. Thus, so this is basically the statement that Sandeep was making. This is a standard Einstein gravity in 4 dimensions without boundary term as an interpretation as a Neumann problem. Yeah. So and also, I'm not going to say much about it. I mean, if you have questions, you can ask me later. So once you have a Neumann problem, you can also construct a Robin problem. So it's if you can't do that just with Dirichlet. Interestingly enough.
For those of us, what is a Robin?
So Robin problem is yeah. So so now that I've been so maybe I think let me just write it carefully. Just yeah. So this is the form of the action. So this is the bulk piece. I'll just write it as Einstein-Hilbert plus this. So this is some arbitrary real number, arbitrary parameter, and then so a term like this, an extra term like this, basically makes so equations of motion plus something of this type. So what I mean, this is basically what a Robin problem is. It's just that typically what you have is a linear combination of the derivative plus the field. When you hold that fixed instead of this thing, then you say that it's a Robin problem. That's just the name. And here I'm saying that when you have a Neumann problem, then you can add a term like this and you get this. But if you start with Dirichlet, there is no simple way to do it, just because of the fact that some trace formulas involving gammas only. You can't do the same thing with pi's. So I don't have a deep understanding of it, but it just so happens that, you could have thought that, what is a good way to say it? So something similar, but with a pi here does not work. That's basically what I'm saying. So you need to go through the Neumann in order to get.
Sorry, let me just get this right.
Yeah.
Sorry. So you're saying by adjusting zeta,
Yeah.
you can get a term like that.
I'm saying that this gives me.
Yeah.
So.
A freedom to,
Yeah.
to then get it.
Yeah, I'm saying that if I add this piece, the variation of this gives me a.
Excuse me, is that really you mean delta gamma ij, right? Oh no. Gamma ij. I guess.
This one?
No,
Yeah, sorry. This is
okay,
yeah.
Yeah, okay, I understand. So
Okay.
now you have the freedom. If you have zeta, you can put this kind of a mixed bound.
Yeah, exactly. And my only point, and it's not particularly maybe interesting or important, is that I know how to do this I have to arrange. So typically in the case of in a particle mechanics type of problem, you can either add a term like this or a term like this to the Dirichlet problem in order to get a Neumann problem. So what I mean is that if you had a Dirichlet problem, you could add this piece, and then you will get something which was psi pi ij plus this type of thing. But if I start with the Neumann guy, I can add a term like this, and I can get an appropriate thing starting from there. But this particular choice only exists for the Neumann case, in the case of gravity, because of the fact that there is no formula analog of this. So this, or okay, something like this does not exist. So it's a technical reason that, I mean, it's not an important statement. I think I spent way too much time talking about it. So, so anyway, so yeah.
I see. Interesting that this Xi coefficient
Yeah.
that gets determined for ADS, correctly renormalized, the
This one.
action. Yes, isn't it? I mean, because the original Gibbons-Hawking term to that.
Oh, I think you're.
To that we have to either counter term.
Yeah.
And different.
That's different. Yeah.
That's additional to this.
Yeah. So that's even if that's right. So this piece is so what is a good way to say this? So I'll show you the renormalized action with Dirichlet, and I'll have it for Neumann. So this piece is, so note that this particular term is d minus 3. These coefficients are here. This is arbitrary. So I'm not talking about what makes this. I'm not talking anything about the renormalizability or the finiteness of the action yet. I'm just talking about the well-defined as a variational principle.
This is at the classical level itself.
Yeah.
You would have this
That's
kind of
right.
stuff, and
Yeah.
then you would further renormalize
Yeah.
this.
Yeah. So, but I mean, I'm not going to talk about the renormalizability of Robin, but I'll just talk about the renormalizability of this guy. But yeah, so.
I mean, I think it's a tricky thing because one way of looking at Robin is you have imposed Neumann in certain coordinates and Dirichlet in other coordinates.
That's right. Yeah.
So it is basically a mix and match of both. And renormalization.
Well, I mean, it's a linear combination of the two. Yeah.
So
Yeah.
it's basically like in some coordinates there is Dirichlet, in some coordinates it's
Yeah.
boundary.
Yeah.
Some components.
Some components.
Yeah.
Sorry,
Yeah.
Some components in
Yeah.
particularly
Yeah.
well-chosen coordinates. You can find some components the
Yeah.
derivative is fixed.
Yeah.
Some components the
That's right.
thing is fixed.
That's right.
And renormalization, basically what it does is, since you are going to pick classical solutions,
Right.
it just makes a classical solution finite,
Yeah.
and that's how it's chosen.
Yeah. Yeah. That's right.
And
Okay.
for the choice where you got pure Neumann, it
Yeah.
had a nice interpretation as doing a Legendre transformation
Right.
on the boundary.
Yeah.
And for the more general mixed, is it some canonical transform? Is it something?
I haven't thought about it. Yeah. So yeah, it could be. Yeah. But so one thing I would say, but I'm in that kind of question is where maybe the fact that Dirichlet does not have a natural, the point is that this action does not have a natural, the psi going to 0 limit exists for this guy, but the psi going to infinity limit is ill-defined. So that's how you can go to the Dirichlet case. That's basically the problem. So yeah, in that sense, I don't know exactly what is the precise meaning of the psi, but it's something.
Yeah, normally a mixture of Dirichlet and Neumann is like Dirichlet plus a double trace operator.
Yeah, yeah,
And the coefficient, the relative coefficient between Dirichlet and Neumann, as which you have shown, that corresponds to switching one, a double trace operator with that.
So in our case, for instance, it will be an irrelevant operator, and it will run, and so that has an interpretation. Yeah, so that's kind of the kind.
So what I mean to say that they are all consistent, and they
Correct.
have an interpretation in the field theory.
Right, but all of those things are very reliant on the fact that you're working around a fixed radius background and the mass ranges of these the scalars and so on. So that is the only thing that.
So you want to do it for the whole.
Yeah, I mean, if at least I would like to understand what is the, meaning, so to speak. But yeah, I don't have anything much.
I'm sorry to ask such a dumb question, but when I did my electrostatics, I only read Jackson in terms of Dirichlet or Neumann boundary
Yeah.
conditions. But mixed also makes sense just for a simple problem like electrostatics. I mean, I'll have to think about it a little bit. If I take a conductor or something, but I don't either force the electric field to be fixed or the potential or something, that's okay. That's a good way to pose.
I would think so. I mean, I'm not sure. So I mean, the number of components is what matters, So I think that's it.
Condition, but it's just physically it's a strange condition. All right.
Yeah. No, but I mean, I think it's precisely in the context of electromagnetism that Robin has first shown up. So I think that's which makes me think that yeah. So yeah, I mean, I considered it only because people asked me, "Can we do this?" when I gave talks. That's the only. I have never heard of Robin either. I mean, I've heard of it, but I never really paid attention to it. So yeah. So I think now we will go on to talk about some, less sure things. Most of the rest of the talk is like much less sure things. So the first thing is that can we say something about, if you have a Neumann type boundary term, what can you do with it for defining a partition function or something like that for gravity? So this is the context in which Gibbons and Hawking first introduced it, and so what they did there. So let me just say in words, so that many of the things that I'm going to say, because it's summary of a couple of papers, is somewhat qualitative, but please feel free to ask questions. So the thing that they did in their paper was that they covariantly computed the Dirichlet action as a free energy, and they did a background subtraction to make things finite, which is kind of ad hoc, but it did the job. And then they in the canonical ensemble. So in the canonical ensemble, it is natural to equate that to this m minus ts minus omega j, and then it turns out that this is the same thing as the SMAR formula for classical black holes if this S is the same thing as A by 4 and T is standard Wittgenstein-Hawking entropy. So this is the original, yeah. It's some formula that looks like m by 2 is m, what is it, Ts minus omega j, something like that. Something like that. It's just an algebraic relation between the parameters of the black hole. So it's yeah. I mean I don't have it here, but it's not, yeah. So that particular one that I wrote might not be quite accurate. So the point is that the thing that I want to emphasize is that the classical black hole thermodynamics, both SMART formula as well as the first law of black hole thermodynamics, they're both very highly classical equations. And the only place where the fact that there is some quantumness goes in is in when you demand. So if you want to define a Euclidean partition function, you are forced to go away from the the real metric, and then if you demand that the metric is your regular, etc., that's where your periodicity of the Euclidean circle comes up, and then you get a specific statement about the temperature. So this is the only point really where the quantum input is coming in. Apart from that, the entire equation, both first law as well as this SMART formula, is completely classical. So our goal will basically be to reproduce that. Can we reproduce that? That's the, we are not going to make very strong statements. We are just going to say that if we do that, we can start with the Neumann partition function and Euclideanize it or complexify it, and look for a saddle which is completely well defined and with no, it's a regular saddle. And if you find a regular saddle, then that would put probably some constraints on the parameters of the metric. And when we do that, are we able to reproduce these two SMART formula and first law? And the answer is yes. And I think it is in some sense trivial, but at the same time, many times it is it's a good check of various things that we do.
So just one thing. So
yeah.
One might wonder in the Gibbons-Hawking paper.
Yeah.
Where in the thermodynamics part of it, where did the Dirichlet condition?
So, but the Dirichlet, they actually do it the very early part. So let me. So the what?
The whole boundary subtraction is a bit of black magic.
Yeah, that is true.
It's only in ADS that it becomes really.
Yeah. And ADS actually we can explicitly do these things and we find perfect matches. So even Neumann. So So I mean in the early part. So this is the early part of their paper. They their discussion of the boundary term is just a cursory thing that they do on the way in order to calculate the action. So what they do is that they have this. They introduce the boundary term. They compute the action by making things Euclidean or complexifying in the case of Kerr or something, and then they get the finite action. Then they just declare that this is the canonical ensemble. So it's not obvious to me that, for instance, this prescription of making things Euclidean or complexifying will always give you a regularity condition in the Euclidean space. And that is always a periodicity condition. So why that particular choice is the most natural Dirichlet is not clear to me. It's really black magic in that sense.
No, but I'm just wondering, in defining things like M and J,
Yeah.
the ADM formula,
Yeah.
there is a certain follow-up condition.
That is true. That is true. But if we don't really need to use the ADM formula. This is just a classical relation between parameters of the black hole solution.
But how do you define M and J?
Correct. I mean, I can use the ADM formula, and I'll use various statements about ADM stuff. But what I'm saying is that I can view these things purely as relationship between parameters in the black hole solution.
Well, I'm just wondering that whether in ADM formula there is some follow-up.
ADM definitely assumes.
Ties up with Dirichlet rather than Neumann.
So
Dirichlet versus Neumann.
Yes.
It has to do with follow-up.
I absolutely agree.
Yes.
Yeah, I agree. So, but what I'm saying is that even there, the equations that they are talking about, I 100% agree that you need a fall off if you want to really interpret that as ADM mass. But what I'm saying is that it's really a relationship between the parameters of the the solution, and that solution is true nonetheless. That equation holds nonetheless. I mean, you can interpret various parts of the parameters as ADM mass or ADM charge, etc., etc. And in ADS, the definition is different. The only point I'm trying to make is that the equation that relates the parameters exists without the claim that any particular combination of them is interpreted as ADM mass or not. That's the only point I'm trying to make. So yeah, I mean, but what you're saying is I completely agree in the sense that like if you really, maybe that's the reason for thinking that this is the natural ensemble. But even then, I mean, like they don't say anything about it in the paper. They just write down this formula and so yeah. Yeah, so that's the point. So here, for instance, this thing here is a canonical. They take it from the canonical ensemble because there's a periodicity in time. They take that to be a canonical ensemble statement. But actually, that periodicity you can get even from microcanonical ensemble. And there is a paper by Brown York who show that because the partition function, if you define it in terms of microcanonical boundary conditions, which has also been investigated, so you find that there is actually a periodicity in time that you get, and the regularity condition comes out even there. So I think it's not a well-known paper, but I think it's a very nice paper of Brown and York where they really they clearly show that the periodicity is just purely from regularity of the Euclidean or complexified section. And but here they take it to be the periodicity, I guess, as a indication that it is canonical ensemble, and they get the correct answer. So, but so the way we will approach this is by doing something different, which is basically that you can look at the covariant way of computing the action and the canonical way of computing the action as two separate entities, and we can explicitly equate the two things that we get. So there is a let's say there is a Dirichlet action. You can compute it using a covariant calculation like Gibbons and Hawking do, and then you can write the same thing in canonical form in terms of the lapse and shift and all that. And you compute that object, and it packages itself nicely into an expression of this form. So this is the way we are going to do it. So so Dirichlet, in the case of the Gibbons-Hawking stuff, it works exactly. When you do this, it works as what they say exactly happens. But we are not particularly necessarily saying that it is. Because we don't know. We know that our ensemble is not canonical. So we need another operational way to do it. So what we do is,
there is that subtraction they had to do.
Right. Yeah. Right.
That came because of the Gibbons-Hawking term evaluated at infinity.
Yeah. So the Gibbons-Hawking term needs a subtraction because it blows up. Yeah.
So it makes sense.
Yeah. So what we do, we do exactly the same sort of thing. So this is what Gibbons and Hawking had, and this is what we do to do the boundary, So this makes everything, and we can check that this is also a well-defined Neumann boundary problem. So, and if you do this, you get the
theta naught is your subtraction.
Subtraction.
Yeah, I mean that's in the Gibbons-Hawking, but that's taken with the flat space metric.
Right.
But when you have some cosmological constant, presumably you have to do some.
That's true. So that's right. For an ADS actually things are much more clear. So because this subtraction is kind of an ad hoc thing that we do. I mean, kind of following what they do, and but interestingly enough, it precisely gives us the smart formula yet again. So maybe that's the saving grace. I don't know. But so so this subtraction is the only thing that I'm really looking for, is that the action becomes finite on shell, and that I don't even think it is. I mean, I don't even think this is necessarily unique. So.
Sorry, and I'm maybe jumping ahead.
Yeah.
You're coming to that, I guess, next.
Yeah,
but,
yeah.
I mean, there I'm worried about what you do about the subtraction story, because your boundary term is different now.
So I can show that this is the term that so if I use the same, this is theta minus theta naught for a flat metric, and I'm just plugging it blindly in here.
Plugging it in. I see. What was the extra boundary term you needed? It was instead of extrinsic curvature, it was pi ij gamma I. No, the extra term was precisely this theta. So this is what I had. So this is the Gibbons-Hawking term with the coefficients are the only thing that are different. Right. Only the coefficient.
Yeah. So
Okay, the above is the Gibbons.
No, this is the Neumann one, and this is the Gibbons-Hawking.
So all that happens
Yeah, so for the mixed one, it is more this thing, but I'll never talk.
So you do the same thing.
Yeah.
Right, thank you. Okay.
Yeah. So,
And then, okay.
yeah, so this is, yeah, so what am I saying here? I can't see. So,
So in this case, in the Neumann case, the theta is fixed, theta naught is different from the fixed theta.
no, theta naught, we take it from the flat space theta naught. We just take it blindly. So, but the thing we can check is that the variational problem still holds. That we can check. So yeah, I mean it's a kind of a DP process, but yeah, but
I see. Even with theta naught, your
yeah,
variation is
it works. Yeah. So that's the, I mean, yeah, that's the non-trivial check we have in the sense that like it has to give a good variational problem and the total action has to be finite. So.
But I can end up taking the theta naught such that this thing does not hold.
Which thing?
Small problem.
Yeah, but I mean, so it's.
Take flat space like it has.
That's right.
It should not correspond to some.
That's right, and yeah, that's yeah. I mean, in principle, always I could do that. Yeah, I think in principle I could even do that here, if I took them. Yeah.
You can subtract out
Yeah.
the geometry completely. I mean,
Yeah.
It has to be flat and
Yeah.
flat throughout. the
Yeah.
space.
That's why the original paper is black match.
No, but at the end of the day, it would come down to computing how you compute charges in.
Right. So we don't have very good answers for that. That's the reason why. I mean, this is also what Gautam was saying, which is basically that what is the ADM mass, etc. But I just want to view it as a statement relating parameters of the solution, and that statement is equally true in both situations. So that's.
17 will have analog in Neumann case.
17 analog in Neumann case. The way in which these things will arrange themselves will be very different actually, especially in ADS. It is surprising that it actually works out. We were not very sure it would, but it's horrendously complex. But in the end, it all becomes again the same Dirichlet type expression. Yeah. So the same smart formula in the first law. Yeah. So. Yeah, so this is a calculation. So we kind of got the inspiration for doing something similar because of this paper of Brown and York, and I think I already mentioned it. So let me go to the next slide. So this is also I mentioned already, which is that the determination of the beta from the regularity of the complexified section is where that's the extra piece on top of the classical stuff, and yeah. So this makes. This is kind of like somewhat speculative statement, but this is, I think it seems very plausible that as long as the variational principle is well defined, you can construct a variational principle that is well defined, and you look at regularity in the Euclidean or complexified section, then you will always be guaranteed to get these two, the first law and the smart formula out of this, which was the original check of Gibbons and Hawking to.
Sorry, I got confused. I mean, so the bulk equations stay the same.
That's right.
So in a sense, the original solution, say the Euclidean Schwarzschild,
Yeah.
will still be a
Yeah.
solution, but the action will be different in general, right? Because
So the action, especially in flat space, gets only contribution from boundary terms.
yeah.
So, but so also there is also another point here, which is basically that okay. Let me show.
But I mean that boundary contribution is changing because your
Yeah.
extrinsic
So
term is changing.
that's right. So let me just flash. So you can ignore this piece. This is this piece is necessary. This is the one that comes from the horizon. So if you write it in canonical language, this is the form of the Dirichlet action. It doesn't matter. None of these specific things really matter. So the only point is that this is the boundary term. This is a piece that comes from the horizon, and this is the bulk piece. So and this piece dies, and this gets a contribution, which is basically the T times S piece, and that's happening deep inside the bulk. And that's where the real thermodynamics somehow comes from. And these pieces, the only thing that they accomplish is to make the variational principle well defined. So, and as long as you have a boundary term that gives you a well defined variational principle, so the thing that you have is, I cannot be 100% sure, but from the examples that I have seen, it looks like it should, all the thermodynamics and those things should go through essentially.
I'm very confused because if I did the calculation, let's take a very simple case,
Yeah.
right? Just Schwarzschild black hole in asymptotically flat
Yeah.
space. Now, if I did the calculation covariantly,
Uh-huh.
R is the curvature is
Uh-huh.
so the bulk term doesn't contribute.
But there is a boundary
There's a boundary
yeah.
term, but the boundary term is different depending on what boundary conditions you choose because you're changing the coefficient of the Gibbons-Hawking. term, right?
But I mean, my subtraction is also this, right? So if this is the thing that gives me the entire bulk contribution in the.
But the coefficient is changing depending on which boundary condition.
Correct. But my right hand side also will change. My right hand side in the sense, if I do the canonical, this is what you are saying is what I call the covariant way of calculating the thing.
So you will not be computing m minus ts.
That's right. So
you
the
compute something else.
exactly.
So what will you compute is, I guess, my question.
So this object on the left hand side, if you can possibly call it the Neumann partition function or something, but that object, whatever I calculate, I'll get some expression, and that will not be of this form. It will have, I didn't put the exact expression here in my slide, but this will be some other form. But the right hand side, in the canonical way, if I calculate, that will also be appropriately modified so that I end up getting the right, the equation remains the same.
But how should you modify it? Sorry.
So I don't have a generic prescription, but I think the idea is just that you should have a well-defined variational principle. This is what I think.
No, but I mean, so canonical ensemble, we all believe that the log of the partition function is over beta times.
Yeah, that's right. So that I don't have an answer to. So I don't know how to think about the Neumann partition. I think it is some kind of mixed ensemble, but all I'm really saying is that I mean these calculations just basically give you the same things, the two things that are typically considered as checks of thermodynamics. That's all I'm saying. But I mean, it's the content of thermodynamics in the case of black holes, I think, is just based on one calculation, which is the fact that the periodicity of the beta gets fixed in some way. So I don't think there is too much content there, but what I'm saying is that much content you can get here as well. So, and the question is, what kind of variational principle leads to what is a good variational principle that you can have? I think that is the. So your question, if I understand it, is basically what are the good kinds of partition functions that you're allowed to have? Isn't that something like that?
Right. I mean, what I was trying to understand was what is the bulk in a very simple case, like say the Schwarzschild and what do the new boundary conditions compute physically? We all believe that the Dirichlet computes the canonical partition.
So I don't have an answer. I don't.
But it's interesting. You say that what you get is sensible. It's just is there a limit where it becomes in the microcanonical? Does it just become E instead of E?
You basically just get entropy. So everything else gets subtracted. In the microcanonical, you just get entropy is the only thing you get.
The energy is just some fixed.
So all of the other things get subtracted out. So I can show you So for instance, in the microcanonical, you keep only this piece. The microcanonical according to Brown and York. So but this piece, this piece and this piece, because the horizon is also there. Yeah, the boundary pieces are all gone because it's effectively a fixed energy, fixed momentum, and fixed some boundary metric type of stuff. That's what you hold.
And very interesting. And as you change your boundary conditions at infinity, are you just playing with the boundary piece, keeping the horizon piece fixed?
Horizon piece stays as it is, and that's where this temperature information comes in.
TS stays fixed, presumably.
Yeah.
And just the coefficient of the mass probably.
Coefficient of the mass, So it can, I mean, it can. So for instance, you can also have, because I haven't told you, but you can also do it in higher dimensions and for Kerr and so on. Right, so all of those things will get extra pieces.
So we'll come to Kerr. Okay, just in the simple case.
Correct. Yeah, that's right.
Presumably, you go from m minus ts to alpha m.
Correct.
Minus ts.
That's right. Yeah. So maybe there is a one parameter family of those kinds of boundary conditions that is possible. But in our case, we find m by 2 or something like that, I think. So some such.
So even though you vary this, Robin. As you go to Robin, you probably get a one parameter.
No. In Neumann, as opposed to.
I understand.
Yeah.
In Neumann, you get one value.
Yeah.
But I was just saying, if you could implement Robin, which you can probably.
Yeah, I think so. I mean, I think I will have a one parameter. Yeah. That's I haven't tried it, but I think it is.
I mean, I'm just what's epsilon?
This epsilon is I mean it's a complex. So there is a k that is coming from. So I haven't written down most of the symbols here. I'm not going to define, and I don't really need. So I'll just say that this comes from the lapse shift breakdown of both the bulk metric and the boundary metric. So this epsilon here is related to a k of the boundary metric over some Newton constant type of thing.
So so this H surface is the what, the horizon?
This is the horizon. So the important pieces here are this is the bulk piece.
B is the sphere at infinity?
Yeah. The whole thing at infinity. There is also a time direction there.
Sorry, yes.
Yeah.
Okay.
And
this is all being done in Lorentzian space?
This is done in Lorentzian. Yeah, but you can also go to Euclidean. This is, for instance, yeah, we can also go to Euclidean, but yeah, this is done in Lorentzian at least. Yeah.
This ST is just the action.
This is the Dirichlet action, the Gibbons-Hawking action. This is the Neumann action. So the only thing that changes is some boundary terms here. So yeah, so and the thing I was emphasizing was that this is the piece that seems to be giving rise to all the interesting thermodynamics. So the boundary terms changing does not seem to matter. Okay, so yeah, I think I already said all these things.
Just speaking.
Yeah.
Just one.
Yeah.
If simply added, the boundary metric was slightly different.
Uh-huh.
Like in the Neumann case, it would be different. Then Euclideanizing it and demanding periodicity close to the horizon of the time circle.
Yeah.
That does not change the temperature in any case. It's the same.
See, so the only thing that matters for the bulk solution, so the thing that we are asking are the bulk solutions, their complexification should be regular. That's what you're asking.
Yeah.
And the bulk solutions are only coming from the bulk equations of motion, right? So the boundary, whatever we do there, as long as the bulk equations of motion have the standard black hole solutions, we'll get those black hole solutions.
But suppose I have two black holes.
Okay.
Let's do it in ADS, because nonetheless you're talking about both ADS and flat. Let's do it in ADS and let's use Krishnan-Graham expansion.
Yeah.
We have boundary
So
metric.
we'll go with that actually. Yeah.
We have boundary metric, and then you have at some order inside z square r square, you will get the Brown-York distance components.
Correct.
It-
Yeah. Yeah.
Now, usually the black hole information of mass and angular momentum you turn up over there.
Uh-huh.
Doesn't function.
Right.
Now I can take two solutions to bulk equations of motion.
Uh-huh.
They differ in the boundary metric.
So
Slightly.
yeah.
Okay.
Uh-huh.
So they do not form.
Uh-huh.
They will not come in Dirichlet case. So if I do the Dirichlet problem,
Yeah.
they will not come in the same setting.
Uh-huh.
Now Euclideanize it and.
Yeah, so I think what you're talking about is the freedom to move GD in Fermat-Graham, right?
Yeah. No,
So-
I'm asking once you Euclideanize it and look at the time circle at the horizon.
But I think in ADS it's a yeah. So this is in principle I think this is something one has to investigate for real in the sense that what in flat space because of you only have like a few black holes, but in ADS if you adjust the GD and if you have matter to support it in some way let's say you could have much more complicated solutions. So I think that so the question of I think the Euclidean regularity will still be the way to determine but I think the values might be different. Yeah.
I'm confused about something very simple. Sorry.
Yeah.
Let's again just take asymptotically flat and just take spherically symmetric
Yeah.
solutions for a moment. So of course we know the Schwarzschild is the only solution.
Right.
But now in the bulk, but suppose I imposed boundary conditions that the momentum
Yeah.
pi ij had
Yeah.
to be some very big value at
Yeah.
infinity.
Yeah.
I would probably have no solution.
Right. I think you're right. Yeah.
So I mean,
So
if you impose suitable Neumann boundary conditions,
Yeah.
the system becomes empty. I mean,
Yeah,
there's no-
I agree. I think the right place to look at this, I think, is basically ADS. I think you might be right. But also notice that we are always talking about vacuum solutions. So we are always talking about vacuum solutions. But I think the question of what kind of solutions are allowed. So here we are looking at existing solutions and how to reproduce the thermodynamics of them from.
No, I understand, but
Yeah.
as you change boundary conditions, of course, the solutions themselves can change, right?
Right. Yeah.
Because the solutions solve the bulk equations.
Yeah, so I don't know what kind of I think because of the Noether theorems are generally I think they assume asymptotic flatness in some form or another.
Yeah.
So here on the other hand, if you put pi ij to be some fixed quantity, it's a little bit like I don't know. I think it is more like you're holding the energy of the system fixed. So in which case I don't know whether the Noether theorems are immediately applicable. I mean So I just don't want to make a strong statement. I'm not sure.
I mean, it just seems like you might do so much violence to
Uh-huh.
the notion of asymptotically flat.
Yeah.
And then on the other hand, the bulk equations by Birkhoff's theorem doesn't give you so much leeway.
Uh-huh.
Maybe it, I don't know. I mean, I don't have intuition.
See the Tij. So Birkhoff's theorem also assumes spherical symmetry.
No, I agree.
Yeah.
So it could be that your boundary conditions are spherically symmetric, but imposing some component of the momentum to not vanish, to be big enough at infinity that you're just not left with any solution, or you're left. I don't know. I'm worried that if you impose quote unquote two artificial boundary conditions, then the system just may not like that. I mean,
Yeah, it's true, but I mean, I think the boundary condition, I don't think it is very artificial in the sense that, like, I don't know what the solution space is. That I agree, but at the same time, it seems like the covariant way of fixing, it's basically the canonical conjugate of the bulk boundary metric. That's what we are holding fixed. So I think that's a fairly natural boundary condition. But I agree with you that in some specific regions of dynamics, maybe there are no solutions. That is possible. But for instance, but also in flat space, we only have two solutions. We only have one solution, curve, and that we also can get here. So I'm saying that, in no-hair theorems also make asymptotically flat with Dirichlet boundary conditions also very restrictive.
and just to understand, here in the calculation you described, the boundary condition you imposed in the Neumann case was that the momentum vanished, right?
So
Was it
the
for it being fixed, but actually the black hole satisfies the condition that it vanishes, right? Am I right or not?
no, I'm not. It can be anything. So what I say is that this object has to be a fixed quantity. That's all I demand for the general problem. But then I look for certain solutions where it can take whatever value it wants. That's the
So let's say I take the black hole.
Yeah.
Say the Schwarzschild
Yeah.
black hole. For it, pi ij probably vanishes at infinity, right?
Not at infinity. I do a cutoff. So this is I'm doing a subtraction.
You have to regulate it,
yeah.
But okay, as a function of the regulator,
Yeah.
what happens to pi ij as the boundary goes to infinity? Does it not vanish?
It has what happens to it exactly? So no, I don't think it has to be.
I'm not sure. The metric is falling off, but you have some square root of gamma. So
I thought that pi ij has the information of mass and charge.
yeah, but it has it in some falling off.
Yeah, it is falling off, but I think the point is that this subtraction is precisely such that all of the relevant information is still there.
But what I mean to say was, suppose instead I had imposed another boundary condition. Let's suppose for a moment it was falling off, and I imposed the boundary condition that pi ij goes to a fixed value, as I'm doing, but not the one the solution we know has, something else.
Yeah,
Then you may be left with no solution.
I agree. Yeah, that is true.
So that would sort of suggest that it's not a very nice thing to do in a theory of gravity.
Could be a different solution.
Could be a different solution.
Right.
Could be different. But I'm just saying, at least for some things we know there are very few solutions. Now maybe even though all the boundary conditions are spherically symmetric, the solution spontaneously breaks it.
No, so I think the statement. So the reason why we are looking at these solutions.
Actually, Birkhoff's theorem, now that I think about it, only assumes spherical symmetry. Right?
Yeah, I think so.
It does assume just that. And then it just
Yeah, I think.
I don't know about. Yeah, I think it is just that. Yeah.
I think turning on pi ij's will turn on gravitational waves in the bulk.
No, that I think is unlikely because if you turn on pi ij, it's a fixed boundary condition.
In ADS boundary condition, it does happen that way because pi ij by Hamilton-Jacobi, pi ij is the same as the boundary value of pi ij becomes the 1.5.
It's precisely the same thing as having what is a well-posed equation of motion problem. Because if I fix either metric at the boundary fixed or I fix the other thing fixed, if I have well-defined equations of motion, then I'm good. Because if gravitational waves are solutions of the equations of motion.
Well, I mean standing some gravitons. See,
So you're saying that there could be standing gravitational waves inside this. That could be.
What
Yeah.
I mean is that if you have pi ij,
Yeah. So,
that's a normalizable mode. The boundary limit of pi ij.
no, but pi ij's normalizability is, I think, a tricky question. So I think, So Sure.
So the expectation value of Tij. Now you are saying that, what is the bulk solution, okay, which corresponds to some finite expectation value of Tij, and we know the answer to that. There's some excited state
Sure.
of the
Yeah.
ADS,
No,
which
but so the,
contains a few gravitons.
right. Yeah. So I mean, but what is the problem?
So as a result, I think the answer to Sandeep's question is that it does exist for at least for perturbative gravitons. You are doing for the whole metric and so on. There I'm a little confused, but for perturbative gravitons, giving pi ij, I think makes sense that it corresponds to some state. Again, in the ABS context, it corresponds to some excited state of the gravity theory. Okay, it's something.
Yeah, I think.
But suppose I said that pi ij, because you allow me to specify it on the boundary for all time.
So, yeah, but so what I am looking at here is just looking at the specific solutions, though.
No, I understand.
Yeah,
And
yeah.
Let's take ADS, right?
Yeah.
This is now a problem where pi ij is specified on the boundary for all time, right? Suppose I take it to be some fixed, time independent. Let's do ADS in global coordinates. Spherically symmetric, fixed time independent constant. Different from what you would get for known solutions. What's the resulting solution? There is no such solution, at least which preserves the spherical symmetry in the equations and in the boundary conditions. So there could be some spontaneously proven. It's not an obvious solution, that's all I'm saying.
Yeah, I think it is a very different problem. I think it's a very different problem. There's no question.
At the boundary, not on some initial slice, right? I mean,
But the initial slice value should be consistent with your boundary conditions.
but if you're only giving, what I mean is that this I know in Euclidean, is that you can just specify some pi ij at the boundary, and there will be some solution corresponding to that, in the sense that you can solve for your perturbative gravitational equations with that boundary condition, that the first subleading term in your the asymptotic expansion is just given by pi, essentially, and that is a solution.
I see. And do you think, just suppose you should go, just suppose we did it in Euclidean space,
Yeah.
do you think the solution would be regular in the interior?
If you just give pi ij, then it's in regular, because you can turn on, you can tune your other boundary condition.
And how is it consistent with Berkoff's theorem, can I ask you?
Because it's not spherically symmetric.
So even though the boundary conditions are spherically symmetric, it's not.
Oh, you were talking about.
But if it is an ADS, ADS has a Birkhoff theorem.
Yeah,
ADS also has a Birkhoff theorem.
ADS is
And but the assumption is what? So the assumption there is that only lambda is there, or there is an assumption about the fall of at infinity,
only spherical symmetry.
and r minus 2 lambda. That's it.
So these solutions are something else. Regular, new solutions, they're all regular.
Euclidean ADS, yeah. So it has
They asymptotically, at least the momentum is spherically symmetric. They're regular in the interior.
So I know this only for gravitons, for probes. That is to say that the Pfefferman-Graham kind of thing, okay, it allows for. I mean, basically there's some Bessel functions. So we have some coefficient times some Bessel function, and some other coefficient times some other Bessel function, and these two guys fall off at different rates. Okay. So if you specify the Dirichlet boundary condition, that fixes the coefficient of the
But in Euclidean space, Gautam, if you require that it is regular in the interior, that fixes the combination of the two Bessels at asymptotic infinity.
That's
right?
correct.
So if you now demand that you only have one and not the other, suppose, then you'll not get a regular solution.
No. By Neumann, you have to do this, that you specify Neumann, and the other thing is fixed.
Other thing is fixed.
Sorry,
Other thing is
free.
Okay.
Free.
That's
Yeah.
That's
Yeah.
I'm sorry.
Yeah.
Other thing is free.
That's what it is.
If you fix both, then there is yeah.
That's the right.
So the relative coefficient between the normalizable and the non-normalizable mode is of course fixed
Yes.
by the
Yes, you're right. I
relativity
said it wrong.
here.
Okay, so your point is what?
I'm a bit confused. If you have pi ij, if you turn on pi ij, how would you do it?
See, there are no gravitons in spherical symmetry. This is the point. Okay, graviton, you'll have no graviton solution period with spherical symmetry. This is how Berkoff's theorem works. See, it's not counter to what you're saying. If you linearize the Einstein equation, the modes you're talking about will not show up in the
as
spherical
not
symmetry.
necessarily.
Yeah, so that's how it's consistent with what you're saying.
Good.
But I'm just saying.
So what was that statement? Can you just repeat what you said just now?
Gautam was talking about, you get gravitons in the Einstein equations when you depart from spherical
Yeah.
symmetry. That's
Yeah.
contendable. So it's not inconsistent.
Yeah.
But if you have pi j, how would you turn it on in spherical symmetric fashion?
I think that's what he's saying, that I think you can't.
Just because of the fact that it's a
It's a two tensor. Isn't it the conjugate? So.
It is the conjugate of the boundary metric, roughly.
Isn't it a radial?
No, there is no.
I thought the extrinsic curve. I mean, it is components of the extrinsic curvature, right?
Yeah, that's right.
I just thought if I take a spherically symmetric metric and I compute the components of the extrinsic curvature, they will be spherically symmetric.
That's right. Yeah, so it's very.
I just thought of turning on pi ij in that way. I mean, it has two legs, but they transform like some, the Lie derivative of that guy is 0. All right, go on, and then never mind.
Like pi r.
Yeah.
That's kind of the thinking.
Or whatever. Yeah, with the two spatial legs, but with Lie derivative.
also from the CFT side, if you were to compute, if you were to construct a state in which the 3-point function with the stress tensor, so the expression value of stress tensor in that state essentially is anything you want. That's the freedom for setting this boundary condition.
Yes, it's very.
That you can achieve probably by choosing a particular state. Because,
Yeah, you're instead of fixing the theory, somehow you're fixing the state.
Because each will have some particular, I mean, the 3-point function will go as something to power delta in the conformal dimension, and as you very know, you will be able to produce any mode of the 1-point function.
So maybe with gravitons, I mean, you can do that.
Like go for it? Yeah. So where were we? Yeah, so yeah, this is just one minor comment, which is that in this same sort of thing will also work for de Sitter because it doesn't have any boundary. So the only thing that gets any kind of contributions is the horizon piece, and that just calculates the entropy, so that works fine. So I think that's so now we'll go on to ADS. Any questions on I guess.
Sorry,
I did not fully understand what it is. Maybe I'll ask you after if you don't mind. But yeah, so now we come to ADS, and so the statement here is, so in asymptotically flat space, we would had to do background subtraction to do this, and in ADS, we know that the Dirichlet problem has a standard holographic renormalization, and the well-defined variational principle while holding the boundary metric fixed is the standard ADS CFT problem, and finite actions for classical solutions are guaranteed by this. So we can try to operationally try and do what one can do for the Neumann case, and there are two natural ways to go about it. We can either proceed by demanding holographic renormalization of our Neumann action with the boundary piece, and we can start with the renormalized Dirichlet action and do our boundary Legendre transform. So these are two strategies in which one might try to construct renormalized Neumann action, and it turns out that both of them give you the same answer. So yeah, so this is kind of related to various questions that have been raised. So note, however, that the interpretation of the result is quite different from the standard ADS CFT picture. We are letting the boundary metric fluctuate while holding the renormalized boundary stress tensor fixed to the boundary. So is it possible that there is some version of holography or something like that, which is where the boundary metric is dynamical? So yeah, I mean, I will not make many comments about it, even though I have some speculations about it. So so this is the beginning comment. And so now now let's set up the standard ADS CFT picture, which is basically that ADS CFT in Pfefferman-Graham metric is what we start with. So this is the context in which we will try to explore Neumann. And so this is the asymptotic form that we'll assume, and this is the standard asymptotically ADS metric. and we introduce a coordinate of this form. So the standard Dirichlet boundary condition is that you fix G0 and all of these guys get fixed except GD. And so GD and G0 together are independent. It's a two derivative equation of motion. So if you fix G0 and GD, the solution is in principle completely fixed. So usually you think of fixing G0 as a boundary condition, and roughly speaking, you can think of what we are doing as fixing GD. So yeah, so that's that. So when the metric solves the Einstein equation, yeah, so this is what I was just saying, is that the higher order coefficients except GD can be determined in terms of derivatives of G0. And so these are all statements which are standard ADS-CFT lore, which is, so G0 is part of the Dirichlet condition. Fixing a specific combination of G0 and G0 plus GD is what amounts to fixing the boundary stress tensor. So yeah. So this is, if you fix both, you have fixed a specific state in the ADS-CFT correspondence. Okay, so now we can start with our Neumann action. So in the case of...
Just to, sorry, I promised to stop saying this, but just to raise the question in the ADS context.
Yeah,
you see,
please.
The reason I keep emphasizing the spherically symmetric case is that you know, then we can do curve, but just for a moment, if everything was spherically symmetric and falling in,
Yeah.
the Schwarzschild black hole is the end point of time evolution.
Right, right.
You know, stuff falls in, you wait, things ring down, and that's the end
Yeah.
point. If your boundary conditions are such that you don't allow for that end point,
Yeah.
you're doing a lot of drastic violence.
I agree.
And in the context of ADS, you see, what you're doing is setting up some boundary conditions so you don't allow the system to thermalize.
Correct. Yeah. So, but I think, yeah.
And okay, that might make sense in ADS, but in asymptotically flat space, I mean, that's
Yeah.
too much violence, you know.
Yeah. So I mean, asymptotically.
That's anyway.
Right, but I think that even you know, like this, the whole background subtraction itself in standard flat space itself, I feel like, I mean, there is nothing really that works in purely in flat space.
Even in ADS, if your boundary conditions allow a horizon to form,
Yeah.
see, it could be that you do so much violence that you don't form a horizon. Then
Right.
things go back and go bounce off the walls forever. Fine.
Yeah.
But if you allow for a horizon to form, then
Yeah.
I would think the system has to settle down, dissipation has to build up. So, I mean, you know, if you
No, I agree that, no, I mean, I agree 100% with everything that you said, but the point is that, you know, I would also say that, you know, it presents itself as a natural boundary condition to explore. So, I mean, you know,
Excellent.
I mean, it's, yeah, so, yeah, I mean, what happens to a box full of gravity if you're allowed to tune the boundary stuff, boundary data? This is, you know, this is how I think about it. I mean, it's, all that we think about it is reflecting boundary condition typically. So at least there is a problem that needs to be solved here. This is, let me leave it at that. So yeah, so yes, so this is you start with the Neumann action. So this is just the bare Neumann action. There is no counter terms or anything like that. We just cut it off just like Skenderis and Solodu can do for a Dirichlet, and we find some particular type of divergence. And our goal will be to systematically add counter terms so that this Neumann action becomes finite on asymptotically ADS backgrounds. By asymptotically ADS, I mean the Pfefferman-Graham. So. And this is precisely what people have done for Dirichlet, and we just blindly follow their this thing, and we find some answers. And here I'm writing it in these renormalized actions in D equal 2, 3, and 4, ADS 3, ADS 4, and ADS 5, in terms of the boundary metric. I mean, if I write it in terms of the Pfefferman-Graham guys, there will be some logarithmic divergence, etc., which also we can keep track of. But I just wanted to write it in a nice way, so I'm ignoring them here. So, and for the black hole calculations that we do, this won't matter. And again, as Sandeep was pointing out, so the black hole calculations, we are relying on the fact that these are solutions that exist, and then we see what we can do with them. And we are not really saying that the phase space of this theory is known. That's not the claim. So, so anyway, so these are, so if you ignore the logarithmic divergence, this is the form of the renormalized actions that we get. And all of these things, the precise form of these terms that show up here are all different from the standard Dirichlet ones. But it turns out that we can, if you calculate these things in the background of the known black hole solutions, they give you the same answer as the Dirichlet case. And first of all, I forgot to emphasize, obviously after you renormalize, these things are finite, and so their values before the cutoff is removed is different from the Dirichlet action, but when the cutoff goes to infinity, they become identical.
Sorry, I didn't understand. So in the asymptotically flat case, I thought in the Dirichlet case you got m minus ts.
M minus ts, yeah.
And in the Neumann case, you just got minus ts.
I think I got m by 2 minus ts,
Oh, okay.
something like that, yeah.
Okay.
So, but here actually it is, it comes out exactly with no problems whatsoever. I get precisely the equations that I get for as I did in the case of Dirichlet. So, and I think it is a property of the solution.
You get exactly, so you would again get m minus ts here.
Yes, yes.
And
So it's a
Dirichlet case.
yeah. So I
You
mean,
get the same thing for
yes, I mean, I don't want to make a too committal a statement, but the thing is that so the form in which these things come out, yeah, I think it is, the general structure is almost identical to that, what we get in the Dirichlet case, but I have to look at my paper before I make it.
It's surprising because you're again going to change the Gibbons-Hawking boundary term
Correct, yeah.
in its coefficient. And that contributes to
Right, but I also get these counter terms and, yeah, so all of these things are playing a role. So I can show you the equation. I mean, it's a,
I'm pretty surprised because I mean the counter term changes as this coefficient changes.
right. So all of those things, but you know, that part, I mean, the calculational aspect of it, I am fairly confident, let's say. The conceptual interpretation might be, you know, we can debate, but I think the calculation is very straightforward.
Answer is always the canonical ensemble partition function, n minus ts.
So the way in which it shows up, the smart formula in ADS is a complicated expression. So I don't want to say that it is just m by 2 is m minus ts. It's a fairly complicated thing involving a and a square and stuff like that, I think.
I just mean the on-shell action when you compute it. Because
The on-shell action is the same thing as what we find in the Dirichlet case.
so that is m minus ts, right?
Yeah.
Because that's the log of the, I mean, that's the free energy.
Right.
Beta times free energy.
Right.
So that, regardless of Neumann or Dirichlet, is the same value here.
That's right. That's right. So I mean, yeah. I mean, the action is the same, but I haven't thought of it in terms of m minus ts on the left-hand side. So yeah.
Just the action,
Yeah.
the free energy.
Yeah. Yeah. So yeah, that is so the action is exactly the same once the cutoff has gone to infinity. That we are 100% sure. So and the right-hand side also, yeah. So the statement that I was talking about was that the right-hand side, if you can write the whole thing in a canonical ADM type of split as well, and then when you calculate it, you get the correct smart formula and the thermodynamics and so on. I think the part of the problem is that I have not written down these equations. I think that those equations were a bit messy, but so I haven't really written them down. But these things are directly calculable in the canonical language, and then you find that they reproduce the correct equations here as well. Okay. So this is the basic reason for one way to understand why that is happening. So because if you're doing the Legendre transform, this is the thing that goes on the right hand side, and this pi AB is nothing but the stress tensor times root gamma, which means that this is the trace anomaly. And the trace anomaly, once you're on shell, this basically gives you a expression of this form. So some central charge times this boundary curvature combinations, and on the black hole solutions that one typically considers, where like the so the asymptotically, so typically the black hole solutions one considers are spherically symmetric or something like that, or the standard Kerr radius solutions. So Kerr radius actually. So and in those cases you can check that these things die out. So that's basically the reason why we are finding the match.
Oh, I see.
So this piece here dies out fast, sufficiently fast.
I thought the Gibbons-Hawking term, I'll have to go back and check. So it doesn't make a finite contribution to the on-shell action, is it?
I have to look at the paper. I don't really know the precise contribution of which term
It's been
went.
a while. Okay, I see. So you're saying basically square root gamma k doesn't make a contribution. So as you change its coefficient, that's the
No. That is not what I'm saying. I am saying that there are other terms also. So there are, if you start with this, so if you start with this is something. This is the Dirichlet case.
the counter term will change.
Yeah, that's what I'm saying.
The net thing is not.
So then there is something here and there is something here, and these two things are very different.
But the bottom, the sum of them.
Some of all of them conspire together in such a way so that, and that's kind of guaranteed by the fact that the two are, well, I mean, it's guaranteed in the sense that it is guaranteed because when we do this, when we systematically make our Neumann action finite, or, by doing this holographic renormalization, the thing that you get happens to be the same that you get by doing a Legendre transform on the renormalized Dirichlet action. And that together with this fact guarantees that they have the same asymptotic form.
Formal invariance is the
Yeah, I suppose, yeah. But yeah, I mean, I see that you're unhappy, but
No, I say it's a striking fact. You're doing your ensemble
Yeah.
as you might have thought.
yeah. But the thing is that we are working with solutions which are naturally preferred in Dirichlet. So as you were saying that we are not really exploring the phase space of the new theory. We are just looking at solutions which are kind of more canonical in the Dirichlet side and checking some things with them. That's all really we are doing. So yeah. Yeah, okay, so I think that's that. So now my talk will get even more speculative. Well, I mean, right now it was not speculative, it is just, yeah. So we can ask whether these fluctuating boundary conditions are merely a classical curiosity or they lead to a consistent quantization of gravity in ADS. So, so one reason why one might think that is because you are finding that the thermodynamics of at least the Dirichlet solution seems to work out in the Neumann case as well. So the crucial question is whether these fluctuations are normalizable. At least, yeah. So yeah. So the problem, as Gautam was saying before, is that problem or the feature is that scalars in a fixed ADS background, there are two modes which we call Dirichlet and Neumann, and they are also, by the way, related by a Legendre transform. Only the Dirichlet mode is typically normalizable. But between this this Breiteln-Launer-Friedman window of masses, you can actually see that they are they're both normalizable, and they are both well-defined quantizations for the scalar field. Okay, so yeah, so when the scalar is not in this specific range, there is only one choice of acceptable normalization, and there is one unique quantization for fixed ADS background. So to understand this better, let us know that the reason why we want normalizability is because ultimately because we want a finite energy kind of condition for fluctuations, and this is yeah. So I can't see from here. So yeah. So the Hilbert space. So in the Hilbert space of the quantum theory, this should be a well-defined state, and this is what we want in a fixed radius background. So when you also let the gravitons be dynamical, so what is the appropriate generalization of that notion? And that has there has been some papers on questions related to that, especially this one paper of Marolf and Compare, and also based on previous work by Wald and Hollands and various other people. And so the basic quantity, which the object, which is the Lee-Wald symplectic structure, and if you ask me too much about it, I have no answers for it. I'll just say some story here, and yeah. So but there is.
I mean, but the basic idea is quite simple, as you say,
Yeah,
right? That
yeah.
if you have a mode which is growing
Yeah.
towards the boundary, and then you have so much volume towards the boundary,
Yeah.
that you can't have fluctuations in that mode.
Yeah, but so the problem is that because of diffeomorphisms, you need to have you need to express that well inside the bulk. So that's if you have a fixed radius background, you can just take that mode and somehow the volume, the size of the mode above the vacuum is kind of a good measure of the energy. But here, for instance, you can't really do that because the metric is also fluctuating. So there is diffeomorphism related issues are there, and that's why this whole
At least in perturbation theory, that
Yeah.
is to say, we have some background and we are looking at small fluctuations.
Uh-huh.
We just want to ask, are modes normalizable or not?
right.
That should be tied to whether they come at a cost in finite energy or not. I agree, once the metric starts back reacting,
Right.
all right.
Right. So I mean, I think.
But there's a sort of mathematical question of defining a norm. There's a standard norm we define.
Yeah.
As per that, is it a normalizable mode?
I think that norm might not be well defined. I'm
So then, we'll have a problem just defining a quantum field with your boundary conditions.
So I'm not even working with a quantum field. I'm talking about metric variations. You see, I mean, like my system is just completely outside the. So, I mean, what you're asking is whether the Lee-Wald symplectic structure is kind of a good proxy for the notion of normalizability in.
mean,
So-
okay, sorry, please just permit me for a minute. You're not doing quantization, but suppose for a moment, okay, you were trying to quantize gravitons.
Yeah.
And you were putting the opposite boundary condition.
Right. Yeah.
My worry would be you have two solutions for gravitons. One goes to constant and one dies at some power. If you take the constant mode and you make it time dependent, you know, the volume also grows fast. You're not going to have a well-defined norm with which to quantize the gravitons. And that brings me, I'm sorry.
Yeah.
So you may conclude there are no gravitons subject to your boundary conditions. You know.
No. Actually, what these people find. So what I find is that, like, my claim at the moment, I mean, this is still tentative. From here on, it's tentative. But my suspicion at the moment is that if I let the boundary fluctuate according to the equations of motion of conformal gravity, I can get normalizable modes inside the bulk. This is what I think at the moment. But and that is based on these statements about the symplectic structure, which I don't have a good intuition for. So but this is what they do for the case when Tij is 0. So in the very beginning of this talk, I showed you, well, so here, for instance, you know, I mentioned the fact that you can work with either q dot equal to 0. So even with the Dirichlet action, you can just set, instead of fixing q to be constant, you can set q dot equal to 0 as a potential boundary condition. So that type of boundary condition for ADS has been investigated by Compare and Marolf. And yeah, so and that's where they use this technology. And you know, even though I'm not 100% familiar with these things, I think that there is a way in which that technology can be modified. And they find that Tij equal to 0 case is normalizable. They use the and normalizable, and these are the two consistency conditions that they need, they claim. And so yeah, so.
So for the Dirichlet boundary condition, on the boundary theory, you just have a asymptotically conformally flat space, and you allow for any one-point function of the stress tensor. While here, in this case, if you were to do a Neumann boundary condition, you allow the boundary to fluctuate. So essentially, you have a gravity theory on the boundary.
That's
but fix a one-point function of the stress tensor.
That's right. So something like that, yeah. So you're talking about whether the q dot analog of the q dot equal to 0 case. That's the case that Compare and Marolf did. And that's typically, the reason for that was that is typically what people call Neumann. Because people, there are various things which are called Neumann, and one of the things that people typically call Neumann is Tij equal to 0 or Tij minus some alpha Gij, something like that is 0. So.
And sorry, just to ask you, if you remember, what is the norm these people find vis-a-vis which these gravitons are normalizable? When you
This is, I was hoping you would not ask me this. No, I mean, I can look at it and, you know, I can explain it in more detail. Because right now, this last part, I'm just telling you the story. So let me say the chronology of how I went into this. So this is something that we did 1.5 years ago. And this is, I left this calculation of the Lee-Wall symplectic structure. And I got to a point where there might be some sign issues. But apart from that, if the conformal gravitons are propagating in the boundary, I am confident that the thing will be normalizable. But I didn't fix those signs. Then I left it for 1.5 years, and I'm reviving it now. So and this is not a subject that I'm too familiar with. So you know, I can't really answer many questions. I'll just tell you the story. I'm very sorry. But yeah, so yeah, so this is all of this is the standard. This is what I was just saying. So this is what Abhijit was just saying. So I'll just go ahead. And yeah, for the Tij equal to 0 case, they find that this they can find a symplectic structure which is both finite and conserved, and that's their definition of a normalizable mode, and that works. And yeah, so this is.
Sorry, what does it mean? So do they find an alternative contribution for the Neumann?
For Tij equal to 0 case, for Tij equal to 0 case, yeah, they do. And they do not find any extra conditions on the boundary gravitons, which is possibly not very surprising.
boundary gravitons.
Yeah.
You mean let's say we do ADS4.
Yeah.
What do you mean by boundary?
So what I mean is G0ij. So for instance, so the statement that I'm making is that if the if D is even, then I find I need to have propagating gravitons on the boundary. The G0ij should have dynamics, and that dynamics is controlled by wild gravity or conformal gravity. And that basically comes from some anomaly terms in this, I didn't present any equation, so it comes from that. So I just plugged it into their machinery, and this is what I get. So I don't understand it, I have to be honest. But I do think that if with some time being spent, I think it can be made tight. I really think so. So yeah, we're already at the end. So
Conformal gravity, I don't know anything about it, but
yeah,
which lives on the boundary.
that's right. That's right. So it basically it's the term that shows up in the trace anomaly. So in any so the dimensions where trace anomaly exists, this is the thing that shows up as the trace anomaly.
So you, like in 2D, would you say R box inverse R? That's the term?
No, it's just the R.
Oh, it's just R.
The thing that shows up as this trace of T. So this
And now promoted to an action.
Promoted to an action. So if the boundaries dynamics is controlled by that term, I can their calculations with minor modifications, it looks like this will also be go through. But yeah, so
You're thinking of R like in three-dimensional areas?
yeah, so R of G0 in D equals 2, and then there is some R mu nu, some complicated mess is there, I can't remember it, some 1/4 or some R square, something like this. This is what it will be in D equals 4.
But R of G0, whatever, then square root of gamma naught, integral, etc., that cannot be a dynamic. That's
Yeah, this is in D equals 2, it's trivial.
It's trivial, but
Yeah, in D equals 4, it's not.
That is A and C.
oh, so
Yeah.
Sorry, D is your bulk.
No, this is my boundary AD. This ADS D plus 1.
So this is,
So ADS D plus 1 should have this guy. This guy should make the G naught of ADS D plus 1 propagate.
so that D is equal to 2 is for
ADS 3.
ADS 3, but there it comes out to be R 1 over box R.
So
I mean, okay, you're saying for when you hold the Tij completely to 0.
Tij to 0. Yeah. So I'm just saying that this is the thing that shows up in the corresponding T mu, this trace anomaly. That's all. The term that shows up in the trace anomaly. That's what I mean.
The term that shows up in the trace
Yeah.
is different.
Yeah. And this is the thing. This is the corresponding thing for in 4 dimensions. So yeah, I mean these are somewhat speculative comments. Yeah. So there are some papers of Rohan and his advisor on related things, which also have some connections to this. But I think I'm maybe going way over time. Oh, it's 1:10. I didn't realize that. So these are some comments. I mean, you can just read them.
So, in this ADS3 work also you took the other boundary condition?
Yeah, so in ADS3 work, what we do is we take a very specific drop-in boundary condition. We free only one component of the boundary metric. Okay, and of course, define a proper variation principle. You need a relevant boundary term. We add the boundary term. Then we look at a class of solutions. Now it turns out only extremal BTZ is allowed, and the rest all are like non-horizon solutions. There's another solution which is given by Strominger. He also frees certain component of the boundary metric. Okay, and he finds extremal BTZ and all other black hole solutions.
So this is the kind of boundary term that they add. So this
And
Ti.
all other black hole solutions. So it's like from
He
the on
finds extremal BTZ is not allowed, but others are.
others are allowed.
And you find
And we find the other way. So
Yeah.
basically it's picking and choosing. So you can indeed pick boundary conditions which do not choose your.
Yeah. So that's, I think I should have thought of it actually, because in 2 dimensions counterexamples are, yeah. So for instance, the solutions that he works with fall into this general category of adding this type of a term where tau or t, this is some new function. So you just add that as an extra piece in your Lagrangian, and then the variational principle will force your delta of Tij to be this Tij, sorry. So the variational principle will give you that.
So in that sense, like in the CFT, you're forcing
Yeah.
stress tensor to have that value.
Yeah.
What you
So ours is slightly different in the sense that we are forcing the stress energy density fixed. That's what we get canonically from this thing. So yours, you're getting the stress tensor equal to some fixed thing that you're putting at the boundary. Yeah. Yeah, I think so. Yeah, I mean there is some more.
And so, what would the general statement be, say, in that we can quantize the graviton with these Neumann boundary conditions, and then even with those boundary conditions, we have normalizable graviton fluctuations, but what we would get is not just a boundary CFT, but that coupled to conformability.
Something like that.
That would be the
Yeah,
same.
something like that. And yeah,
And 1 point function on stress tensor will be fixed.
yeah, yeah,
I imagine. Or
yeah.
I don't know the theory.
No. I mean, this is my
So the theory for
feel also, but I haven't. Yeah.
for ADS3, I mean, it does turn out to be R1 over box R as the boundary theory.
Oh, it's not R.
No, it's not R. R is what is.
I agree. So
Fixed
then
to
that's
the
a
system.
statement.
So what
Yeah,
we
and that is
do
the analog of the yeah.
Yeah, so one can match the symmetries of what the asymptotic symmetries that you get over here and the symmetries of R1 over box R in different coordinates.
And this is very different from the quantization that comes for scalar fields with Neumann boundary conditions, which is the alternative quantization
Yeah.
in which the
Yeah.
operators you take the other set of operators
Yeah.
whose conformal dimensions are d minus delta
Yeah.
and so on.
And then there is a condition on the
So
the
that
range.
happens only for some range
Right.
classes. But you were saying here that although it's not that kind of quantization, but there is a quantization.
So there is one. So this is the statement that I just kind of began saying here. So if you deform the theory by a double trace deformation, you know that it starts flowing, and then in such a situation, at least in the case of scalars, for instance, people have done. I mean, there are papers by Witten and various papers exist, which are kind of the statement is that there is a SL2C duality.
However, outside of that window,
Uh-huh.
so this double trace flow goes forever.
That's right.
It
That's
does
right.
not
I
end
agree.
up anywhere.
I agree.
Outside of that window, if you try to impose the other boundary condition, can you won't get anything sensible.
There is no quant.
So
There is only one fixed point of the RG, and that is the.
So the statement there is that the flow is staying as a quantum field theory, right? I mean, it's.
But you never reach what would have been the other fixed point, which is the entry fixed point.
I agree with all of these things. This is.
here, if you're getting away, it's somehow because of
No, I'm not getting away. I'm actually paying the price.
Okay, but the price is that which you may not. I mean, I think for a scalar outside the window, there's no price you
For
can get away.
yeah, for a scalar there is no chance.
So it's only gravity.
Gravitons, I am hoping that maybe there is something interesting can happen here.
But that's all, I mean, because it's also saturating the unitary form, right? It's not very far. It's not a very
Is
low.
gravity exactly something?
Yeah.
It's D and 0 for stress tensor and
Okay, so
graviton.
it's like a scalar on the threshold.
On the threshold.
Yeah.
Okay, so maybe for scalars on the threshold. Good, I don't remember whether you have to be within. Okay, yeah, but alright, I see. Way above, it's clear you can't because it's not necessary.
Be like here in the middle.
Yeah. Okay. I see.
Thank you.